Hello there. Welcome to the Learning of Engineering tutorial video lecture. In this video lecture, we are trying to discussing about the cantilever beam, which is subjected to the uniform distributed load. In connection of the previous video lectures, we have seen the cantilever beam is going to be subjected to the point loads. So we have seen how the behavior of the cantilever when it is subjected to the point loads. Now we will see the uniform distributed load. Then what is the uniform distributed load in this case? That means that load is going to be spreaded over the area or the surface of the member, certain length it is going to be consist. So that area, suppose you can take the pressure. So that pressure, suppose we are going to be immerse a bottle inside the water, so that the surface of that bottle is going to be subjected to the uniform distributed load over there. And here also we can see here, so that I have taken AB is going to be the beam. Just I am assuming here the AB is going to be the beam, and I had applied the load at uniformly distributed. Can you see the distributed load is going to be spreaded over the length of the beam, and it has some area also it is occupied, but we are considering only in the 2-dimensional. So then what we are going to do? We need to find out the standard thing is that the shear force as well as the bending moments we need to be considered. So in order to find out this one, and we know the uniform distributed load is going to be spreaded, that's going to be omega, that's going to be Newton per meter we are going to be taking. So that means that W is going to be, small w is going to be the load, and it is spreaded over the length, that is Newton per meter. Now I want to find out the shear force at any section of the beam. We know that is going to be your shear force and the bending moments. Then how could you find out? So in order to find out that, I have to consider at one section of the beam, right? I am going to be considering this is going to be your section of the beam. It is located at a distance of x. So that's going to be small x I am going to be considering, and this point I am going to be considering as this point C. There you can see I considered one section of the beam. It is located at a distance of x from the point B, and that section point I am going to be considered as the C. Now what I am going to do, I want to find out the shear force as well as the bending moments. Then how could you calculate the shear force and bending moment? As we know, it is going to be spreaded over a length, right? That we need to be converted into the point load, so that I can calculate the shear forces as well as the bending. We know the shear forces units is going to be the newtons, and bending moments units is going to be Newton per meter, Newton meter. Can you see? But the load is there in the Newton per meter is there. So what I am going to do, I am going to be taking over this span. That means I am going to be finding the rate of loading at the point C. So right, that I am going to be saying Fx I am going to be considering. The Fx is equal to, what is the formula? We need to get the Newton's units for the shear force. So then here that's going to be, it is the spreaded, the magnitude of the height of this one is going to be the load is going to be we have, that's going to be omega. So then this units is going to be Newton per meter. Then I am going to be multiplying over the length of the beam. That means going to be for the section it is the length is the x. So that I am going to be taking the x. So for this one, this is going to be Newton per meter, and x also the meter. This is going to be cancelled. Then finally Fx is equal to the load into the distance we got it. So can you see? So from this one, I can find out the different parameters. What is the shear force at B and shear force at A, or any point of the section also I can calculate. So now I am going to be taking, for the case 1, x is equal to 0. If I am substituting x is equal to 0, then that point will become here, it is the starting point, that's going to be FB. FB into the load into the distance, then finally we are getting the 0. Right? It means that whenever the uniform distributed load is there, whenever the starting point of the B will become 0, shear forces are there. In the second case, what I am going to do, x is equal to L I am substituting. When I am substituting x is equal to L, then this will become FA. So that means we are calculating the shear force at point A. So that is equal to W into L we are going to be taking. Then finally, this is going to be the shear force, right? That is going to be W into L, we got it. the shear force at B is equal to 0. Once I am going to be calculated this one, now I will try to go to find out the bending moments here. So then how could you calculate the bending moments? So there we can see the bending moments how similarly we are going to be taking from the section. So that I am going to say mx. We know that's going to be the force into perpendicular distance we generally used to be considered as the moment. So at mx distance is equal to. So then what I am going to do, if I am going to be considering only this, the length of the beam, and this is going to be the magnitude is going to be acting there. So that I am going to be taking Fx, that is the shear force is going to be existed into perpendicular distance we need to take it. So suppose I am going to be converting this into the point load. Then what is the exact line of action of the point load? Suppose this is going to be your line of action. So that the distance I am going to be taking x by 2 I am going to be considering. Right? If I am going to be taking the x by 2, that's going to be the location of the center of the distributed load. Right? So this is going to be your observation point, and this is going to be the point of the line of action of your load is passing. Right? So that I am going to be getting here. So what I am going to do, Fx is equal to, we know, W into x, that's into x by 2 we are getting. That finally I am writing mx is equal to wx square by 2 we got it. So this is going to be the moment is existed at this section. As we know, the x is the variable, from 0 to L length it is going to be varying. So I am going to be trying to take the moments for that. What I am going to do for the boundary condition for this first case is equal to x is equal to 0. When x is equal to 0, I can try to find out the bending moments at B. That I am going to be say MB is equal to W into, that is the distributed load, into 0 square by 2. The finally I am getting the 0. The bending moment at B is equal to 0, and shear force also at B is equal to 0. So now I am going to be taking the second one, x is equal to L. If I am going to be substituting in this equation, that is going to be MA is equal to, that means load into L square by 2 we got it. So this is the magnitude of the moment is existed at A. Once we are going to be calculating this, the shear force and bending moments at A and B, now I am trying to draw the shear force diagram, then I can find out at any length of that. So for this one I can take the scale, right? I hope you know how to take the scale. Now we are going to be trying to draw the shear force and bending momentum diagram. So here we can see, as we told, first we need to take the different sections of the beam. So this is going to be your section A, right? And this is going to be your section C, and this is going to be your section B. Now I am going to be drawing the axis of the member. Right? This is going to be your axis of the member, and here also I am going to be taking the axis of the member. So there we can see. So now first one I can use for the shear force diagram, second one is the bending momentum diagram I am using. This is the point B, this is the C, and this is the A. As we know, the shear force diagram that I am going to be taking, that when x is equal to 0, that means the shear force is equal to 0. And similarly, the shear force at x, that is going to be the point C. So that is going to be Wx, we got it. And similarly, at A is equal to W into L, we got it. So now what I am going to do, I am going to be draw the line for that. So how we are going to be draw? So that I am going to be taking here, that's going to be inclined line. So this is going to be representing your SFD for the cantilever beam. So there we can see, now we got it here because the distribution load is going to be uniform over there. So that's why we got the triangle over there. So now I want to draw the bending momentum diagram. How could you take the bending moment? As we know, whenever the things are moving in the clockwise direction, already we told that's going to be the negative. Whenever the things are moving in the opposite direction, that is going to be the positive. All these cases are going to be, you are getting mx is equal to minus, and ma is, this is also minus we are getting. So on that basis, the bending moments at B is equal to 0. At Mx is equal to, that's going to be Wx something is we do have, and similarly at L distance, that is the Ma is equal to WL square by 2. So as we can see, the line of the order, we can see this member is going to be subjected to the inclined position. When these inclines are there in the shear force, in the bending momentum diagram, we are getting the curved lines. So that's going to be your parabolic curve we are going to be getting like this. So that we are going to be draw, so like this. This is going to be your parabolic curve, assume. So this is the point A, C and the B. Now we can see this is called bending momentum diagram. Now as for the scale, if I want to find out the bending moment and the shear force at the point D, suppose. So what I am going to do, I am going to be taking the projection of this line which is passing through these points. So whenever this point is going to be coming, this magnitude, this is the height is going to be the magnitude that is representing your shear force, and this magnitude is going to be, this height is representing the magnitude, and then we can find out the bending moments. So I hope you are able to understand how to develop the mathematical model for the shear force as well as the bending moment. For this one we have taken the section and then we developed the model by substituting the boundary condition. Once we are getting, then I am going to be draw the shear force as well as the bending momentum diagram. On that basis, once it is going to be the values we are substituting by using the scale, any point on the beam we can calculate the shear force without any further calculations of these parameters. So in continuation of this video, we are going to do one or two problems in the next video lectures. So until, stay tuned. Thank you.